Okay, so basically during phase changes, your temperature are going to remain the same. However, when you're taking pressure into consideration, that's going to also change. Okay, so when you look at a phase diagram, you're basically looking at temperature versus pressure. In some cases, there are going to be other types that you guys will talk about if you go into material science. But basically, you're looking at the transition of each of the stages based upon temperature and pressure. So like, for instance, this is the phase diagram. This is a phase diagram for water. If we take a look at this phase diagram here, you have this line here, which basically is showing us the distinction between the solid and the liquid. We have this line here showing us the distinction between a liquid and a gas. The point where the two meet, this is called your triple point. So this is the point where you have your solid, your liquid, and your gas in equilibrium. So you have all of them existing in the same, at that state and at that temperature and pressure, okay? And so on this phase diagram, we're kind of showing you that transition. So when you're going from a solid to a liquid, it's melting. When you go from a liquid to a solid, it's freezing. When you go from liquid to a gas, it's vaporization. When you go from a gas to liquid, it's condensation. And when you go from a solid to gas, sublimation. And when you go from a gas to a solid, deposition. There is a point called the critical point. The critical point is where the line between a liquid and a gas kind of gets screwed up. And certain things, certain compounds will actually go into what we call, what we would call a super critical fluid. And I'll kind of explain that a little bit later. But the critical point is where that line is dissolved, in a sense. And we'll talk more about that. So if energy is going to be absorbed during a phase change, is that going to be endothermic or exothermic? So if it takes energy to sit there and go from one stage to the other stage, is that going to be endothermic or exothermic?
Endothermic.
Okay, endothermic. Okay, so if I'm going from, let's say, a solid to a liquid, the energy that it takes in there, that will be an endothermic reaction, right? Because we have to put energy in to sit there and get from that solid to a liquid, right? So that also is going to mean that the energy is going to be used to break up those intermolecular forces. Okay. So this could be done by two manners. One manner, it could be done by putting work on the system, right? So we could be adding energy in by putting work on the system. So that's like by putting pressure in. Or it could be done by an increase in temperature. And so that would be putting heat into the system. Okay, so both of them could actually be done to sit there and serve the same purpose. Okay, so if energy is being released from a phase, then in that case, that's going to be an exothermic reaction. And that energy is going to be associated with the energy that it takes that is being released from the formation of those forces. And then it also could be in the sense of having less work on a system. So that's that pressure component, or heat. So okay, so here's a phase diagram. You need to be familiar with how to read a phase diagram. So for instance, it's not too hard. Plotting. So if I have 10 degrees Celsius and 50 kilopascals. So I would go up to 50 kilopascals. And then I would go over to 10 degrees Celsius. That's roughly 10. Okay, so what phase would this guy be?
Water.
Water, okay. So liquid phase. Yep. Okay, Mauricio, do you mind doing B for me? Taylor, can you do C? Gracia, can you do D? Angelia, can you do E? And Michaela, can you do F? Oops. Oops, I did 10. I should minus 10, so it should be a solid. Like I've been drinking. Gracia, are you there?
Yes, I'm just trying to write on this thing. Let me see if I can zoom in. I don't know if I'm right.
But Taylor, you were right at first.
Oh, okay.
Yeah. Yeah, because if this is 50 right here, 10 is just going to be a little bit lower. And if you look at it, so you were right at first. It's not quite to scale. And Gracia,
Yes.
so we have 80 degrees Celsius. So 80 is about, we'll say about right here. And we have about 5 degrees.
So then it would be gas, wouldn't it?
Yep.
Yeah, because I was looking at the graph and I was like, no, this thing looks wrong.
Yeah. Okay. Simple. Piece of cake.
Yes.
Good. You may see one of those on the exam. Okay. So supercritical fluid is basically like a single phase where like the boundary line between this liquid and gas basically disappear. And so you're going to get it kind of like an intermediate between a gaseous liquid state. Okay, so it's going to have properties of kind of like both, right? So it's going to have a density that's kind of like a gas, that's typical of a gas. It's going to be able to fill a container. Sorry, it's going to have a density that's kind of like a liquid, but it's going to be able to fill a container like a gas does. It's not going to have any surface tension associated with it. It's going to have very low viscosity. It's going to be able to dissolve solvents, not solvents, solutes, non-volatile solutes. And it basically can penetrate very small openings in a solid mixture. So it's great for removing soluble components. So in industry, they take advantage of supercritical fluid. So they basically use carbon dioxide. To take a look at carbon dioxide, this is the phase diagram of carbon dioxide. And you guys can see that's where your supercritical fluid is located at. So, excuse me, at temperatures, basically temperatures above 25, and then pressures that are at least 10K, 10,000 kilodaltons. So under high pressure, and then and average temperature, you're able to sit there and get carbon dioxide, and it's in a supercritical phase. Now, this can actually be used to sit there and take the caffeine out of coffee beans, right? So in the coffee industry, what they do is they'll put in their beans, and then they'll put in supercritical fluid of carbon dioxide, and it'll actually flow through there. And then so the carbon dioxide will be able to penetrate the beans and remove the caffeine out of it, because caffeine has both that polar region and a non-polar region, and carbon dioxide takes advantage of that non-polar region with dispersionary forces. And so you're extracting all of the caffeine out of the system. So then you get a twofer. So you get decaffeinated beans that you can sell on the market, and then you also get caffeine, right? Questions, concerns, Cash? Good. Okay, so now let's talk about solids. Solids have two types of organization. So one is a crystalline solid, and one is an amorphous solid. And a crystalline solid is it has order associated with it. So it has a nice arrangement that is defined by repeating patterns. Amorphous is random. It has random organization. Okay. So if we have silicone dioxide in its natural state, it forms a crystalline structure. But if we get a hold of silicone dioxide and we rapidly cool the molten silicone dioxide, it'll actually start forming amorphous structures. So it'll be like fused silica, right? And so it's no longer organized. It doesn't have that nice arrangement. It doesn't have that nice crystalline structure. So the types of solids that we could have an ionic solid. You guys are very familiar with that, salt. So basically you're using the positive and your negative ions. They're being held together by electrostatic forces. Those solids are basically hard, they're brittle, they have a high melting point, and they do not conduct electricity unless it's melted or molten, okay? Or is dissolved in a solution, okay, like water. Okay, so we know that sodium chloride, when it's salt, you can't use it to sit there and conduct electricity. But when you put it in solution, when you put it in water, when it's salt water, the ions are able to separate and then it's able to conduct electricity. Metallic solids. Metallic solids are basically, they're going to be like crystalline solids as well. And so all they basically are, they're going to be a uniform distribution of atomic nuclei in a sea of delocalized electrons. So if you guys remember when we talked about a metallic bond, so we have sodium. We know that sodium has that one valence electron, right? So what sodium will do when it's by itself, it'll pretend that it's positive and get rid of that electron. And literally it'll put that electron right next to it and pretend like that electron is a negative charge and it's attracted to it. Okay, so what happens is that all the sodiums in sodium metal actually do that. And so they're interacting by electrostatic forces, in a sense, by delocalizing that electron, that valence electrons that they have. Okay, does that make sense? You guys remember that from metallic bonds?
Yeah.
Okay. So things that we know about metals. Metals are great at conducting heat, so they're very thermoconductive, and they're also great at conducting electricity. That's why we use them, metals in our wires, right, for conducting electricity. They have a metallic luster to them. They're malleable. They vary in strength, so we have some that are really strong and then some that are really weak. And they have various melting temperatures. We know that mercury is a liquid at room temperature, right? So we know that they vary in that regard too, from that scale. And then we know that like something like steel is a solid at room and very strong. We have covalent network solids. So these solids are basically held together by a network of covalent bonds. And so diamond is just basically carbon bonded to carbon, carbon. And it's forming a three-dimensional structure, as you guys can kind of see here, to sit there and form that diamond molecule. Okay, where graphite forms a planar structure, and then they have loose connections at the ends of the planes. Okay, and so that allows us, like when you write, use a pencil lead is that basically graphite. So it leaves a layer of those carbon sheets on your paper, and so that's what you actually see on the paper. So these covalent networks are going to be relatively strong. They're going to be characterized by their hardness, their strength, and their melting temperature. Okay. We have molecular solids. Molecular solids are going to be neutral molecules. They're going to be bound by the intermolecular forces. That's what's going to be keeping them together. They're going to have varying strength. So we're going to have some that are semi-strong and some that are really weak. So for example, we have ice, dry ice, sucrose, and iodine. And so here we have carbon dioxide and iodine. Carbon dioxide's melting temperature is -78 degrees Celsius. And iodine's melting temperature is at 114 degrees Celsius. So quite different on that scale too. So this is just a table kind of summarizing all of the properties of those solids and their distinctions and things to that extent. So chemistry has been utilized to develop new materials for the future, things that are stronger, that behave better, that can work on smaller scales. And so some of those items, such as the buckyball, the nanotubes, and stacked sheets, are currently being used in development now. And so we've come a long way in terms of that development of things. And so and part of that is making use of what we know about the characteristics of those chemicals and the types of bonds that we're forming. So let me tell you a little bit more about some crystals. So we have talked about crystal defects. So there are 3 types of impurities or defects in crystals. One of them is called vacancies. Vacancies are when you have an open spot entirely. Let's see. So this here is a vacancy. Basically, let's say this was all iron, right? So these are all of the iron atoms. This would be one iron atom that would be missing. Okay, so that is an example of vacancy. We have substitution impurities. Substitution impurities means that we substituted one of those atoms for something else. It can be an atom, it can be a molecule or an ion. It doesn't matter, but we substituted for some other atom. So in this case, instead of having iron there, we put magnesium. So we have magnesium there. And so we'd have that characteristic of magnesium sitting in that, substitute in that spot, okay? So we can also have a substitution that's bigger. And so if it's bigger, it can actually cause warping of that area. And so then you're losing some of the structure associated with it in that regard. The other and the last one is called interstitial impurities. And so basically you have an element or an atom that is really, really small that it can actually fit between two or basically these 4 atoms of whatever we're looking at, or 4 molecules of what we're looking at. And so a lot of times we kind of use that in terms of adding some characteristics. So for instance, substitutions, talk about some of the substitutions. We can add certain substitutions that can improve the characteristics of metal. Like for instance, steel, stainless steel. So if we use iron and we add in chromium, well, chromium doesn't rust, iron does rust. But if we add chromium in with our steel, then we get stainless steel, meaning that it won't rust on us. Okay, so we're using some of that characteristics to make improvements to what we're looking at. And so often we'll do what we call doping of a solid. And that's just basically adding something in intentionally so to give us some type of quality. Okay, are you guys good? Does that make sense?
Is that kind of what they did with bronze?
Yes, yes. Yeah, so bronze is an alloy, right? And so basically they actually do dope it. If I remember correctly, it's copper, zinc, and last metal, silver. Copper, zinc, and silver. And it actually gives that nice little color to it because of the characteristics. It's also pretty firm compared to each of those metals independently, so it adds some strength to it as well too. So this is actually being used, doping is actually being used in real life. So silica chip technology basically uses doping. So basically we have a chip that is basically silica. So it's a covalent network. solid, and it's been we add arsenic if we want it to be kind of like a negative type, because arsenic basically has one more electron than silicon, and then boron has one less electron than silicon. So then that's more like a positive type of effect. So you'll have in the industry, you have combinations of N types and P types semiconductors, some that have been doped with arsenic, some that have been doped with boron. And then sometimes you have silica that has a combination of both in the same chip itself. So this basically is going to be used for converting from AC to DC in terms of electrical devices. Okay, so now I'm going to have to go to Mr. Abella's slides. And I'm sorry, you know, like I said, he did me a solid, because I haven't had a chance to go through all my slides here. I can find it. Oh, there you go. Oh, that's chapter 6. You need that one. But it's not the one I want right now. There we go. Okay. Okay, so the next thing I want to talk about is like the lattice structure of our crystalline solids. So because they're organized in a very systematic way, they have what we call that unit cell. The unit cell is basically a three-dimensional construct that is used for the repetition of that particular crystalline structure, right? So it's going to repeat the unit cell, and it's going to have a certain organization to it. And we'll kind of talk about that. I'll show you some pictures. Now, the simplest unit cell is going to be a cube, and that's the one that we're going to start off with. There are other types. They're a lot more complicated. We won't talk about those at all today. Okay, so the unit cell, the cubic unit cell, so this is basically showing us. So at each corner here is where an atom is going to be located at. So this would serve as a unit. And so in theory, when you have the metal together, you'll have this unit, then you have another unit on top, another unit on top, another unit here, unit back there, unit back there. So to kind of give you an idea of what that unit cell kind of looks like, it's that repetition. So there are three types that we mainly talk about, three of them that actually occur in nature. And okay. I think I got in trouble. So the three types of unit cells are, like I said, we have the simple cubed. And so that's where you have at every four corners of the cube, you have an atom located. And that's kind of shown here at the bottom. So we have a body centered. And so basically in the very center of the cube, we have another atom there. So we have atoms located on all 4 points. And then in the very center of the cube, we also have another atom. We have a face centered, so we have atoms on the 4 corners, and then every side, we have another atom, okay? Do you guys see the difference between all 3?
Yeah.
Okay, so an example of how this guy kind of is used, we kind of use it to determine the radius of atoms, or we can use it to determine the radius of let's say a compound that's interacting together in a cubic structure. Okay, so the way that we would do that is, we know back when we were in algebra, we learned about the Pythagorean Theorem, a squared plus b squared equals c squared, where if we have a right triangle, this is A, this is B, and then that's C. You guys remember that?
Yeah.
Okay, so this is a perfect cube. So then A and B are going to be exactly the same. So then we just have A squared plus A squared equals C. And in this situation, C is going to be represented. So this is a face-centered cube. So this is on one side of the face. So if we looked at the radius, we have, that will be an R. This will be 2R, because that's the diameter of that circle. And then this guy would just also be an R. So altogether, that's going to be 4R. Okay. So if we plug that into our equation here, so we know that, as I said, A and B are going to be equal to each other. So you just get A squared plus B squared. And then 4R squared. So then that gives me 6R. So then that means that, break this down, A squared equals 8 over R squared. And if we solve for R, we have A over 2 square root of 2 equals R. And then in this case, our value for R is given to us up here. So we're talking about silver. If we wanted to calculate the radius of silver, this is the length of the side. So then we'd be able to just plug that into, that length is A. This is equal to A. We'd plug it into this equation here, and then we'll get our answer. Piece of cake. So if it were me, I would be familiar with how to do this in the case of a simple cube, or in the case of a body cube, or a body-centered cube. Okay, so we did it just for this one. So you want to be familiar with the other two, just in case. Okay, so X-ray crystallography. X-ray crystallography is often used to determine the structure of things. One of the major things that were discovered over the last several years is the crystalline structure of DNA. So they basically use X-ray crystallography to kind of get the structure of the double helix. We kind of also talked about it earlier during the semester, where they actually use it to crystallize the structure and to determine the structure of the HIV protease protein. So X-ray diffraction is basically pretty important for what we do. And it basically works in the context of we're shooting waves, because X-rays are just waves, and they're going to be shot at the structure that we're looking at. And so we can actually use that diffraction to sit there and give us an idea of what that chemical or compound or substance looks like. Because what happens is that those X-rays will hit the nucleus and then it'll bounce off, and then in a comparable angle. So the angle coming in goes off. So then that'll allow us to sit there and collect images and then kind of figure out what that structure is going to end up looking like at the end. Okay. So here is an example of a crystalline structure. So that's going to be like part of our unit cell. So the X-rays are going to be coming in. And so as the X-rays come in, they're going to be coming in at a certain angle. That angle is going to be comparable to the angle that it's going to be reflected off once it hits that molecule. Okay, the same thing can be said about X-rays coming in here. It's going to come off and reflect. So then we can play with angles. So if we play with the angles, we basically get to the point where this angle is going to reflect off here. And this angle will be the same angle that is going to be associated with the wavelength, which is represented by this and this. So it'd be the sum of xy plus yz is going to equal lambda. And if we look at our angle, we know that back in those old days, sine is going to be equal to opposite over hypotenuse. Okay, so in this case, opposite is going to be that distance between x and y. Sorry, sine theta. And d represents the distance between that one molecule, this one molecule, and the other molecule, which also would be our hypotenuse. So if the distance between x and y and z are going to be the same, so then we could plug in this for both of these if we solve for the xy. So we can say sine theta d sine theta equals xy. We plug this in for both of these, so then we get d sine theta plus d sine theta equals lambda. And so we'll say lambda is going to equal 2d sine theta. Okay, so then we can kind of use that to solve an equation. So this guy is called Bragg's equation. This lambda equals 2d sine theta. Let me move that. Okay, I can erase all this. Okay, so how can we use this? Okay, so an example of us using it is by knowing that the X-ray angle relative to the crystal and the wavelength of the X-ray, the distance between the atom can be calculated. Calculate the distance between the atoms of copper with an incident angle of 14.22 degrees and a wavelength of 1.54 times 10 to the minus 10 meters. What am I going to do?
Can we draw a picture?
I'm going to draw my picture. So that's going to be my D. This is going to be my wavelength. So they want me to calculate my D, and then that's going to be my angle. So what am I going to do? How am I going to calculate it? I have lambda. Lambda is what?
2d sine.
2d sine. Okay, so that's what lambda equals. But what does lambda stand for?
Is it the wavelength?
It's the wavelength, right? So since it's the wavelength, then I can solve for D because that's what I want. I want the distance. So then D is going to equal lambda over 2 sine. Theta. So if I plug in those values, lambda is, this is my lambda. It's 1.54 times 10 to the minus 10 meters divided by 2, and then sine of 14.22. What do you guys get? Yep, I'm gonna have to rely on you because my phone is dead.
I got 7.72
7.72
times 10 to the negative 11.
times 10 to the negative 11. So are you using degrees and not radians when you calculate sine?
That's a good question. I'm using radians.
Yeah, I got the same answer, and I just realized I was using radian too.
Okay.
Okay, I got 3.13 times 10 to the negative 10.
Okay, that sounds better. And that's meters. Piece of cake?
Eh.
Let me take a screenshot just in case I forget.
So Angelia or Leah, are you gonna ask me if you're gonna have to memorize this equation?
I hope not, but I want to think so.
No, you're not gonna have to memorize the equation. I'm gonna give you an equation sheet, so.
Thank you.
Okay. Okay, so let's talk about the exam real quick before we start on to the next chapter. So your exam is gonna cover chapters 7, 8. It's gonna be focused primarily on chapter 7, 8, 10, and a little bit of 11. Okay.
Okay.
A combination of all the flavors.
That's right. Let's see. What's your notes? Okay, so chapter 11. So we're going to be talking about the solution process. We're going to talk about electrolytes. We're going to talk about solubility, and we're going to talk about colligative properties, and then colloids. Okay, so the dissolution properties. So the definition of a solution, we kind of talked about this before. It doesn't necessarily have to be liquids. It could be a solution of gas. But basically, you have a solute dissolved in a solvent. The solute is the one that is the least abundant. The solvent is the one that's most abundant. And so you're dissolving the solute and the solvent. Okay. If the solvent isn't been defined, it's going to be assumed to be water, or we're going to say aqueous, AQ, to let us know that it is water. Okay. Soluble covalent solutions, they're going to basically exist as individually dispersed particles throughout the solution. So to be a solution, it's going to have to be evenly dispersed throughout the solution. It can't be, you know, a mixture. We could have a mixture where you have like dirt drop down to the bottom and then you have water up top. That's a mixture. So for it to be a solution, it's going to have to be dispersed throughout the solution. Okay. So for example, we have water and alcohol, or water and methanol. Okay. So if we put methanol in water, the water basically keeps the methanol suspended in solution. Okay, so then we end up saying the methanol liquid, we put in water, we make it aqueous. So we'll say CH3OH, it's going to be a liquid. Then as we add water to it, it becomes CHOH, and then AQ to let us know that it's been dissolved in liquid. Okay, again, we're looking at the methanol as that solute. It's going to be important, but we're putting it in the solvent, which is the water. Okay. When we put ions in, or soluble ions in solution, they're going to dissociate. So like when we put ionic compounds or ionic bonded molecules into water, a lot of them dissociate into their ionic components. And we've talked about that early on in last semester. So if we have potassium dichromate, we put it in solution. Well, initially it goes in solution. Eventually it breaks up into its ionic components. So we end up with the 2 potassium ions, and then we end up with the chromate ion. I'm sorry, dichromate ion. Okay, so the energy that's involved in solvation, or basically making solutions. So for forming a solution, you basically need a high enough energy to get over the threshold. Otherwise, the solution isn't going to form. It's not going to be suspended. Okay, so there is a threshold level. Okay, many solutions are going to form spontaneous, right? So in those cases, no energy has to be put into the situation. The threshold is really low, so we have a very, very, very low threshold energy. So, or there is an increase in the driving force called entropy. Entropy is basically, it describes disorder of a system. Low disorder basically means that things are highly organized, while high disorder means that the system is totally random, it's totally disorganized, okay? So a system that is going from low entropy to high entropy can be done by a driving force, okay? So going from a low entropy, so low disorder, to high disorder can be a driving force. Okay, so for example, barium hydroxide has a low solubility in water. And it's often defined as being insoluble. But if we put heat with barium hydroxide, it'll actually dissolve and be soluble in water, forming the ions. Okay. So in that context, we're pushing it to go into that. We're pushing it by adding some energy to get over that threshold. Okay. If the intermolecular forces of a substances are very similar to each other, so the intermolecular forces of the solute and the solvent are very similar to each other, so it's going to basically require no energy to sit there and have those guys to go in solution. Okay, so if they both have polar forces, so they have dipole, then they're going to go into solution together. So that's kind of like in the case of, let's say, methanol and water, right? So both of those they both have hydrogen bonds, and so they require no energy to sit there and incorporate with each other. Okay, sodium hydroxide has a high solubility in water. This guy is going to form spontaneously, releasing heat. Okay, because it's an exothermic reaction, and that's because of the increase in enthalpy due to the ion dissociation. Where the ammonium nitrate that's used in a coal pack is also going to form spontaneously, but in that case, it's going to be an endothermic reaction. So it's going to be taking in energy from the environment. And so in that case, that requires some energy that's going to be absorbed from the atmosphere. And then that's because the driving force isn't going to be enough. The enthalpy driving force isn't going to be enough to sit there and push it over that threshold. So it has to get that energy from somewhere else. Okay, so electrolytes. So electrolytes are basically, they're going to be ions that are going to be in solution. That's what it boils down to. Okay. An electrolytic solution is going to be something that can conduct electricity. So often if we put those ions in solution, they dissolve. You have that plus and you have minus charge. It's going to be able to conduct electricity. Okay. So the ions are going to physically dissociate from each other or result in a chemical reaction. Let's see, an ion that dissociates 100%, so you have the ions completely dissolved, So then that's going to be a strong electrolyte. A weak electrolyte is going to be an ion that doesn't completely dissolve. So that are going to kind of stay together. So like, for instance, we talked about barium hydroxide. So at room temperature, barium hydroxide is going to be a weak electrolyte. But if we heat it up, then it becomes a strong electrolyte because we could get that complete dissociation. So, sorry, solutions that don't have a significant electrical conductivity, they are non-electrolytes. They're not going to conduct electricity. Right? So the most common electrolytes are going to involve ion dipole solutions. So like when we're in the case of water, you have an ion like sodium plus and chlorine minus that are going to be in water. Okay, so solubility is basically going to be determined by the table that is provided. We kind of provided that table back last semester. Okay, and the thing about that table, there's a couple things that you always want to remember is group one, and we'll talk about it here in a minute. Group one metals are always going to be soluble, right? So anything that's with group one metals is going to be soluble. Okay, solubility of a solution is kind of generally talked about in that table that we're going to be talking about. I'm going to show you in a second. So things are kind of qualitatively described. So we'll say that a solution is saturated. So a saturated solution basically means that you have the maximum solubility. An unsaturated solution means that you're not quite to the max yet. And then you also have what we call a supersaturated solution. A supersaturated solution is you've set up a condition so that you can exceed the maximum solubility. So you've added some temperature to it, or you've done something unique to that solution to allow more things to initially go in there, give it more than that maximum solubility. Okay. Gas solubility is going to be dependent on pressure of gases. And so we're going to talk about Henry's law, and that's going to be associated with gases. Henry's law is associated with gases. You can kind of think of me. I'm full of hot air, so associated with gases, right?
Hey.
Okay, so let's talk about that solubility table, if I can get my computer to work. Okay, so anything with ammonium is always going to be soluble. Ammonium chloride, soluble. Ammonium nitride, soluble. Okay, so anything with ammonia is going to be soluble. Anything with nitrates, going to be soluble. Okay, so nitrates are always going to be soluble. Most acetates are soluble except for aluminum acetate and silver 1 or silver acetate. Okay, so those aren't going to be soluble. Your perchlorates and your chlorates are always going to be soluble. Your nitrites are going to be soluble except for silver 1. Most of your chlorides, bromides, and iodines are soluble except for silver 1, mercury 1, and lead 2. Most of your fluorides are going to be soluble except for group 2 metals and lead 2. And we also know that hydrogen sulfide, it is soluble, but it doesn't completely dissociate, right? So it has weak solubility, hydrofluoric acid. Most sulfates are going to be soluble except for calcium, strontium, barium, and silver 1, silver 2, silver 1, mercury 2, and lead 2. Many of the phosphates are going to be insoluble, except for when they're with group 1 metals or with ammonia. Our carbonates are going to be insoluble, except for group 1 and ammonium. Our phosphates are going to be insoluble, except for group 1 and ammonia. Most of our sulfides are insoluble, except for group 1 and ammonia. Hydrogen, or I should say, hydrogen dihydrogen sulfide is insoluble, or hydrogen sulfide is insoluble. Most hydroxides are going to be insoluble, except for group 1 and ammonia and barium, the barium ion. Most oxides are insoluble, and then all acids are going to be considered soluble, but they may not completely dissociate, except for the strong acids, which completely dissociate as part of them being a strong acid. Most gases are considered to be insoluble, such as hydrogen sulfide, methane, ammonia, and oxygen. Okay, Henry's law. So Henry's law basically says that the concentration, the solute concentration of the dissolved gas is going to be equal to a proportionality constant, K, and that's usually going to be given to you, or you're going to be calculating it one or the other, and the partial pressure of the gas. Okay. So now this works when there's no reaction of the dissolved solute with the solvent. So to calculate the solubility of nitrogen gas in water when the partial pressure of nitrogen above water is 1.10 atm at 0 degrees Celsius, and the solubility of nitrogen in water is 8.21 times 10 to the minus 4th molar at 0 degrees Celsius with a nitrogen pressure above water of 0.790 atm. Okay, what am I going to do?
Can you go back to the formula really fast?
I sure can. Okay, did you get it? Oops. Okay, so what is going to be the first thing that I'm going to do?
For the nitrogen, do you plug that in into Cg?
For the nitrogen, do I plug that into Cg?
The 8.21 times 10 to the negative 4?
So yes, we are going to use that. But we know that we have two conditions happening. Both of these are occurring at 0 degrees, so temperature is not going to be a factor. They're both at 0. The only thing that's going to be changing is pressure, those partial pressures, right? So under one condition, this concentration is at this partial pressure. So we want to calculate the solubility, which is the concentration that we're looking at this partial pressure. So to do that, we're going to have to use the equation, right? So if we say that CG1 equals K PG1. Okay, and then we have CG2 equals PG2. Sorry, I forgot my K. We know that K is a constant. K is going to be the same under both circumstances. So we could solve these for K. So we'll have CG 1 over PG 1 equals K. Same thing down here. CG 2 over PG 2. So then I could just say CG 2 over PG 2 equals CG 1 over PG 1. Okay. So then what do I need to do now? So if this is CG1 and this is PG1 and then this is PG2, what do I need to do?
Plug them in.
I could plug them in. And solve for CG2. So we'll get PG2 over PG1 times CG1. And then we just plug them in. 1.10 ATM over 0.790 ATM times 8.21 times 10 to the minus 4. Molar. So we get CG equals, I have to rely on your calculations.
I don't know if this is right, but I got 5.89 times 10 to the negative 4.
That sounds right.
Okay. And then how did you differentiate?
Actually,
Oh.
let me make sure
Okay.
that's maybe not quite. I think we have it inverted. CG. That's right. Two, one, one. Okay. Shouldn't that be? Click, check. So 1.10 divided by 0.79 times 8.21. Actually, it should be CG2 should equal 1.14 times 10 to the third. Minus third, sorry, molar.
Okay.
Okay, now what were you going to ask?
How did you differentiate between PG1 and PG2, or like CG1 or CG2?
Because they're at two different conditions. Well, they're at the same temperature, but we're looking at one under one partial pressure, and then we're looking at the other one at another partial pressure. But the constant is always going to be the same. K is always going to be the same in both cases. Does that make sense?
Yeah.
Because K is a constant. It's always going to be the same. Okay, so colligative properties. So colligative properties are just basically the properties it's going to be a change in the physical properties due to an amount of solvent dissolved in, due to the amount of solute dissolved in a solvent. Okay, so like for instance, you guys added salt to water, and in one case, and you added magnesium sulfate to water in another case. So those guys, that addition of those solutes to your water solution is going to have an effect on those properties. It's going to change the properties, like that boiling temperature, right? Did you guys observe that?
Yeah.
So, for example, we're going to be looking at, so when you add a solvent to, if you add a solute to a solution or a solvent, it's going to change that solute's boiling point by increasing it in most cases. So you're going to get an elevation of the boiling point. It's going to decrease the freezing point, and it's also going to have an effect on the osmotic pressure by increasing it. Okay. So or decreasing it, sorry. So to measure the colligative properties, you're going to be using molar fraction or molarity, or sorry, molality. You guys remember molality from last semester? We talked about concentrations.
Kind of.
Okay, well, we'll see. So molality is basically moles of solute over kilograms of solvent. That's going to be our molality. Or we can use mole fraction. Mole fraction is going to be the fraction of one, the solute, let's say, divided by the number of moles of the solute divided by number of moles of the solute plus the moles of the solvent. Okay, and this is a typo. I need to fix this slide. So the sum of the mole fractions of A, XA, and XB is going to have to be equal to 1 because it's a fraction. So this should be XA and XB. Okay. Okay, so Raoult's law basically sets up the equation so that the mole fraction of the solute times the vapor pressure of that pure mole fraction of the solvent and the vapor pressure of that pure solvent is going to be equal to the vapor pressure of the solution. Okay. So if we wanted to calculate in this question here, the vapor pressure of a solution containing 53.6 grams of glycerin dissolved in 133.7 grams of ethanol is 113 torr at 40 degrees Celsius. Calculate the vapor pressure of pure ethanol at 40 degrees Celsius. So where am I going to start? What is the equation? You guys remember?
Mole solute over kilogram solvent. Oh, wait, no, not that one.
Moles. So mole fraction of the solvent times the partial pressure of the solvent or the vapor pressure of the solvent is going to be equal to the vapor pressure of the solution. Okay, so what is the mole fraction of the solvent? How do we calculate that?
Do we do 53.6 over 133.7 grams?
Is that going to give me my moles fraction? And would that even be a fraction? Or would that...
So the 1 mole of C3H8O3, then
So how do I calculate the
divide
number?
by the grams.
Okay, so I divide this by the molar mass, as you were telling me,
Yeah.
because we need to convert it to moles, right? So if we convert it to moles, what is the molar mass of glycerin? 3 times 12, 8 times 1, and 3 times 16. I know it's been a while since you guys did anything like this.
$92.
So 92 grams. Over 1 mole.
Point 576.
Okay. Okay, now what about ethanol? So we have 133 grams, 133.7 grams of ethanol.
I think the molar mass is 46. Let me check. Okay, 46 grams, and then 2.906.
You said 906?
Or
So then
9.
9. So we're looking at the molar mass of the solvent. So then X is going to be equal to solvent. That's going to be equal to the ethanol, 2.91 over 2.91 plus 0.576.
Point 834 or 835.
You said 835. Okay. So then we just plug that in. Well, we'll solve for the P solvent. So we have P solution over X solvent and that's going to equal P solvent. This guy is going to be 113 torr divided by 0.835. What do you guys get?
$135.3.
You said 135.3.
Yeah.
So 135, 3 sig figs, torr. Okay, piece of cake. Is that excitement that I hear from you guys? Excellent. I like excitement. Okay, so are you guys ready for your lab?
Yes.
Okay, so we're gonna meet in the lab room. I need to go get all my stuff together.